In this video, I want to look at the singular values of a matrix as well as the singular value decomposition. Let's let A be an m by n matrix, so it does not need to be a square matrix, just any general matrix. The first property that we need is that A and A transpose A have the same null space. We also have that A and A transpose A have the same row space. While they don't have the same column space, A transpose and A transpose A have the same column space. And A transpose A have the same rank. So these are going to be helpful for us in our study of singular values. And there are two more important properties about this A transpose A that we need to consider. A transpose A is orthogonally diagonalizable. So we can find an orthogonal diagonalization of A transpose A. And finally, the eigenvalues of A transpose A are non-negative. So they can be 0 or positive, but they cannot be a negative value. And so now that we have looked at these properties of A transpose A, let's talk about what a singular value actually is. So to define a singular value, let's consider A to be an m by n matrix. And then what we want to find lambda 1, lambda 2, all the way through lambda n, which are going to be the eigenvalues of A transpose A. So we want to actually find these non-negative eigenvalues of A transpose A. Then the singular values of a matrix A, we denote by sigma. Sigma 1 is the square root of lambda 1. Sigma 2 is the square root of lambda 2, etc. So the singular values are actually the square roots of the eigenvalues of A transpose A. Let's look at an example. Here is my matrix A. So A transpose, the first column turns into the first row, the second column turns into the second row, times A. And recall when we multiply matrices, we multiply rows by columns. So this would be 1 plus 0 plus 1, that's 2. 1 plus 0 plus 0 is 1. 1 plus 0 plus 0 is 1. And then 1 plus 1 plus 0 is 2. And then I want to find the eigenvalues of that matrix. So we subtract lambda from the diagonal. So that would be 2 minus lambda times 2 minus lambda, minus 1 is equal to 0. This actually simplifies to lambda squared minus 4 lambda plus 3 equal to 0, which factors into lambda minus 3 lambda minus 1. So my eigenvalues are 3 and 1. So my singular values, which I'm going to denote by SV, is the square root of 3 and the square root of 1, which is just 1. And these singular values can actually tell us a lot about a matrix. For an example, the singular values here tells me that this matrix has a rank of 2. The dimension of the column space is 2. Because the rank is equal to the number of non-zero singular values. We have 2 non-zero singular values, so the rank of this matrix is 2. I now want to look at finding the singular value decomposition, which has a lot of applications in data compression. Essentially, I'm going to let A once again be an m by n matrix. And the rank is going to be equal to k. So it has k non-zero singular values. What I want is to find a decomposition where A is equal to U times S times V transpose. U is going to be an orthogonal m by n matrix, m by m matrix. V is a different orthogonal matrix, this time an n by n. And S is going to be an n by n matrix that essentially looks like a diagonal matrix in the upper left corner and then zeros all around it. Let's go back to the matrix we were looking at before. It can be very complicated and time-consuming to calculate a singular value decomposition by hand. So instead, I'm going to talk about how to do it on MatLab. We're going to start by having a bracket with a U, an S, and a V in it. And then we're going to use the command svd of our matrix A. And this will output 3 matrices, where A is equal to U times S times V transpose. It'll output our singular value decomposition. To demonstrate this, I have MatLab open in my browser. I start by typing in the matrix A, 1, 1, 0, 1, 1, 0. We then do square brackets with U, S, V equal to, and the command is svd A. And then we get our matrices U, S, and V. So if I look at that matrix S, those eigenvalues are the square root of 3 and 1. That's the things on the diagonal of S. And so this would be my singular value decomposition. And we can double check it by doing U times S times V transpose. And we see that we get back to the matrix that we started with.